Our first idea was just to have a heated blanket rolled up in a box, and you'd stick a piece of clothing, whatever you want to heat up, into the heated up blanket, roll it up, and we would hope that it would just heat it evenly throughout. But we ended up not doing that because it just had way too many tangling cords, too many ways to mess up, and it wasn't like optimal for the user at all. And some other items on the list were layered heating elements folded into a box, which for the same reason is horrible design because we had like too many folding things and it didn't work. And the other two that seemed promising was the rack and the oven-like heating, but the rack was already taken with like a towel heating rack that people already use. So we decided to go with the oven-like heater as it probably work better.
So at the beginning of the year, we surveyed all the student body and the staff, and we got 132 responses from that. And 66.7% of those responses liked our product and were interested in purchasing a product similar to that.
Solution. So we created this model on a computer software program called Inventor. And our idea was to originally just have a box with heating on the bottom. And it just had a simple lid with hinges.
So here's a little bit of detail into how the entire project works.
So the main component of our project is the hot plate. It's just a copper sheet with 6 thermoelectric coolers pasted underneath it. And they're just these little ceramic tiles that on one side gets super hot and the other side gets really cold. And we use the hot side to warm our copper plate.
So we ended up putting fans in our design. It wasn't our original idea, but we thought it would like help with the flow of heat through the project. So there's actually a heat sink, which is the metal thing below the fan, that basically takes heat from our thermoelectric coolers underneath them, and it disperses it evenly, and then the fan was there to pull the heat off of the heat sink. And we thought that this would just move the heat a little bit more in the box and like blow evenly throughout the clothes. And then right now the fan is just open, but we ended up putting like a metal grate over the top of it, which is down there. So the clothes couldn't get in and get tangled or just create a mess inside the box.
So this is how we powered our project. It's really simple, it's just a power supply. We hook it up to our extension cord, which is now attached to something else, which we'll get into a little bit later. But the power goes in, the power goes out, and it basically transfers the right amount of current that we want for our thermoelectric coolers and our fans.
So this is the wiring schematic for our project. It's relatively simple. It just has a power supply, and then we have fans and thermoelectric coolers hooked up to that. And then we have a timer that acts as the switch for the whole circuit.
So here is the timer. This is kind of like just like a Christmas light timer. You guys have probably seen this before, but it basically, you set the time for when you want it to run. This way, if you want to set it for the morning, you'll be able to set it when you go to bed, and then it'll automatically turn on and maybe heat up clothes before you go to work or something. This also acts as like a safety measure to prevent if you just run it for hours on end. This is a way to just run it safely and just the enough amount of time you need.
So this is a little bit more on the timer mechanism. We have a Velcro to the side of our box, and that's just for user ease pretty much. You just put it on the side, you can not deal with the cord. And a little bit on how the dial works. The dial spins around and very slowly at 15-minute intervals, so you can set a 15-minute interval at any time you want. And there's a little pin that is pushed when the notch you select is pushed down. It goes over it and turns it on.
So these are the hinges and latches we used for our box. They're just normal steel hinges and latches. And the point of the latches is to keep the lid firmly on top of our seal, so it creates a nice seal to trap in all the heat and warm the clothes.
So one of our problems before was to keep the heat inside the box. So we had to come up with more and more ideas to make the box stay hot instead of just losing all the heat just outside the box.
So the first and most obvious way to do this is just insulation. So our method of insulation, which is already in the classroom available for us, was this blue foam, and we covered the edges with blue rectangles, and it allowed us to just keep lots of heat in. And it also underneath the copper, so it's insulating the top and the bottom. And then on top of the blue foam, so it looks better, we have just wood planks, which act as more heat, keeping it.
This is the heat resistant sealant we used. We just used it to seal all of our edges and seal the thermoelectric coolers in place. It has a really high heat resistance, so we don't have to worry about it melting or anything.
So the lid, this is pretty simple. It's just we needed something to keep the heat down, and obviously the latches hold it down tightly so the heat stays in warm.
So I crashed my dad's 96 GMC Sierra into the side of an Amazon Prime truck. So we took the weather strips off of it, which is the perfect way to keep our lid sealed nice and on the box. So here's some images of us drying it after it was cleaned off because it got really dirty, and it just runs along the edges of the box. And we had some problems keeping it on, but we fastened it with some screws, so it should work now.
So this next couple slides will be about our final product.
So as you can see in the middle of the door or the lid, we have a hinge, and that was supposed to just automatically open the top. Like once you create contact, it's just a smooth automatic opening. But we had problems where for it to be able to be closed tightly without warping, the angle of the lid was too small, so we couldn't get the close in easily. So we just decided to take that out, but we painted it to finish nicely, and we just wanted to make it look more professional.
So along the way, we encountered lots of problems, and the next few slides go into that.
So it's kind of hard to tell what's going on in this photo, but this is us cutting out the weather strips, and those are really difficult to cut out because it's a really tough rubber and there's metal wire in it. So we had to really hold it down to cut it.
So we had problems with screws sticking outside the wood. Our wood was so thin that no screws would go in it and just stay inside the wood, so we had to cut them down with a metal saw. And I ended up cutting myself twice with the saw because they were just so hard to cut. But we got them down to this short little stub, and we put hot glue over them so it prevents any scratching.
Yeah, the paint covers it up now, so you can't even tell. And when Bo cut himself twice, he was bleeding everywhere, and he kept cutting them off. So the other problem, it's really simple, but it's the latch. We screwed it on too close to the middle of the lid, so we couldn't make it a 90-degree angle. So we had to file out little divots for the metal to go down into, so it could secure onto the box.
So as Bo stated earlier, we used to have we were going to use a pneumatic hinge at the beginning of the year, but then we decided to use a spring one, but that didn't work either because it warped the lid of our box, and also it was just too much trouble to keep it in, so we got rid of it.
There were also screws again sticking through the top because our wood is so thin, so we couldn't really avoid that problem too well.
And the pneumatic hinges we ordered like 2 of them in the mail, and only 1 came, and it took like so much pressure to push down, it wasn't even useful.
So the inside of our box, some of the thermoelectric coolers actually burnt out, so they wouldn't even heat up anymore. And it was actually 5 of them that burnt out of the 6. So we had to order more of them. And this was a problem because we just got them on Sunday. So we quickly put them in, but it was very hard to access the inside of the box. The copper was very malleable, and when we pulled it apart, it just bent it like crazy. So we had to flatten that out again, and it was hard to get into because we put the interiors of the box inside on top of the copper. So it was just a big mess.
So here's some wrapping remarks.
So our personal final thoughts on our project. We think ours was a little bit simpler. Compared to the other groups who had really complex designs, ours is pretty simple. And we could always make improvements to it. We did cut, it used to be twice as tall, but we cut it down. But it's still kind of a little bulky, and we could increase its efficiency by we could use different heating techniques, and those might work better. And then the look of our box, it's kind of plain. It's just a wooden box with some copper in it. And then the accessibility of our box could have been increased because we were not able to install the new thermoelectric coolers when they broke, and that was kind of an issue.
And like Gage said, with the simple design, it was tough at the beginning of the year because we were trying to figure out something that we could do to create a project for a full year. And this ended up being a little easier than we thought it would. So we kind of finished this design a month ago. So we're just making some changes with the looks of the box. And what we would have done differently, we spray painted the inside of the box. This isn't too much of a problem now, but at first it smelled like paint every single time we turned it on, and it was toxic. The copper components underneath the copper is not actually insulated, so we could have insulated that to keep more heat in. We definitely could have bought more thermoelectric coolers because obviously some of them burnt out, and maybe we could have had more on the bottom to just add to the heat. And like we said before, a more involved project. We didn't think it would be too easy, but.
Thank you all for coming to see our project and our presentation. If anyone has any questions, feel free to ask them.
I heard you say a couple times that you had wood that was thin. Why did you continue to go with the thin wood, which created problems with the screws and the warping top? Did you think about any other material?
So we did think about other material, but we did the wood because it's lightweight, and we wanted lightweight because we were thinking about doing metal, but I feel like that would be too heavy for as compact as we want it to be. We could have done plastic, I guess, but then we would have had to worry about maybe possibly breaking because wood bends easily, I guess. Any other questions?
So what you referred to as the thermoelectric coolers, those are like LTA devices, right?
Yeah.
So why did you guys pick that rather than doing like a normal, like a resistive heater like you have in a heated blanket? It seems like you created a bigger challenge for yourself using those, which are sometimes used to like generate energy based on temperature differentials rather than heating something.
Yeah, we actually did a lot of research about that, and we wanted to try the thermoelectric coolers because we found a website that we kind of created a heat plate with them. We would have done wires, but I feel like that could have been problematic if like we just had a copper bottom. So I mean, we definitely could do other things. It's kind of a simple design, so you can, any way you can create heat would work, I guess.
And I mean, definitely for the bottom, I think the thermoelectric coolers were good for just the bottom, as they like allow the top to get heated while the cold is separated and pushed to the bottom. But definitely for the round, where we have the fans, we could use an actual heating mechanism instead. So yeah, you're right.
Again, I don't know very much about engineering either, but were you worried at all about wood catching fire if it got too hot in there?
We actually did research on that too, and we found the temperature and voltage that the thermoelectric coolers needed to prevent wood from starting on fire, and they don't get nearly hot enough to actually start wood on fire.
Yeah, we ran some tests with some heat guns, and they didn't get too hot. They were just the right temperature for us.
Which is about 110 degrees. Any other questions?
All right, thanks guys.